Okay, Assalamu alaikum. Today we are going to do integration of trigonometric functions, the past paper questions of the P3 course. Okay, let's start with the first question. It says show that 2 sin x plus cos x the whole square can be written in this form. Okay, let's apply the formula here. 2 sin x plus cos x the whole square. Okay, I'm going to apply the formula a square plus 2ab plus b square. So it'll be 4 sine square x a square plus 2ab. So 2 times 2 sine x into cos x plus cos square x. Okay. Okay. I can write this in terms of cos of 2x. Okay, so it'll be 4 into 1 minus cos of 2x divided by 2. I'm using the basic double angle identities for cos of 2x. Cos of 2x we know is cos square x minus sine square x, or cos of 2x can also be equal to 2 cos square x minus 1, or cos of 2x is equals to 1 minus 2 sine square x. Now, if you make sine square x the subject from here, you will end up having 1 minus cos of 2x divided by 2. So that's what I'm using here. Okay. Plus 4 times sine x cos x plus cos square x. Now, if you make cos square x the subject from here, you will get 1 plus cos of 2x divided by 2. Now, I'm using the double angle formula for sine of 2x also here. Sine of 2x equals to 2 sine x cos x. So, if I want a Fourier, because here instead of 2 sine x cos x, you have 4 sine x cos x. That means you're multiplying it by 2. So, if you're multiplying this side by 2, you have to multiply this also by 2. So, 2 sine 2x equals to 4 sine x cos x. Okay. So, let's simplify this further. 2 1 times, 2 2 times. I'm left with 2 minus 2 cos 2x plus, instead of 4 sin x cos x, I'm writing 2 sin 2x plus 1 upon 2 plus half cos of 2x. Now I'm adding the constants. Half plus 2 plus half is a 5 upon 2. Okay, I'm taking both the terms as cos of 2x. It's negative 2 cos 2x plus half cos 2x. So negative 2 plus half is negative 3 upon 2. So negative 3 upon 2 cos of 2x plus 2 sine of 2x. This is what we had to prove for the first part of the question, which is proved now. Now, moving on to the second part of the question, hence find the exact value of, they're asking us to integrate this and putting the boundaries. Now we know that this is exactly equivalent to this, so we will integrate this. Okay, for the second part of the question, we are going to integrate 5/2 plus 2 sine 2x minus 3 upon 2 cos of 2x dot dx, and the boundaries are pi by 4 and 0. Let's integrate this. It will be 5/2x plus, integration of sine is negative cos, so I'm going to write negative 2 cos 2x divided by 2. Integration of cos is positive sine x, so it will be negative 3 upon 2 only, sine of 2x divided by 2. Okay, so it's 5/2. I have to apply the boundaries of pi by 4 and 0. Minus cos of 2x minus 3 upon 4 sine of 2x with the boundaries pi by 4 and 0. Okay, so 5/2 pi by 4 minus cos 2 pi by 4 minus 3 upon 4 sine 2 pi by 4 minus. Now, if you plug in 0 in this will become 0. This is cos of 0. Cos of 0 we know is a 1. So, 0 minus 1 minus 3 upon 4. Sine of 0 is 0 only. So, this whole bracket is going to be just minus 1 in this bracket. Okay, let's simplify. 5 pi by 8. Okay. Minus cos, when you simplify this, you are getting a cos pi by 2. Cos pi by 2 is actually 0. Minus 3 upon 4. This is sin pi by 2, which is a 1. Plus 1. Okay, so the final answer is 5 upon 8 pi plus 3 upon 4. Sorry, negative 3 upon 4 plus 1. So it's going to be minus 5 upon 8 pi. 1 minus 3 upon 4 is positive 1 upon 4. This is the answer. Okay. This is the answer to question number 11 then. Sorry, this is equals to, so this is also equals to. Final answer is 5 upon 8 pi plus 1 upon 4. Question number 12. By differentiating cos x upon sin x, show that if y equals to quarter of x, then dy by dx equals to this. Okay, we know that this is equals to quarter of x. Quarter of x is cos x upon sin x. Okay, so if we take u upon v, so we know that u equals to cos x. So u dash is going to be differentiation of cos x is negative sin x. V is sin x. V dash is going to be cos x. Okay, so we apply the formula dy by dx equals to v, which is sin x, u dash, which is minus sin x, minus u, which is cos x, and u dash, v dash, which is cos x. Okay, upon v square, which is sin square x. Okay, let's simplify. This is minus sin square x minus cos square x divided by sin square x. If I take out minus as common, I'll be left with sin square x plus cos square x, which is 1 upon sin square x, which is actually minus 1 upon sin square x, which is minus 1 upon cos x square x. So we're done with the first part of the question, where we had to prove that the derivative of cos of x upon sin of x is equals to minus cos x square x. Now in the next part, by expressing cot square x in terms of cos x square x and using the result of part 1, show that, okay, if you have to differentiate, if you want to differentiate cot square x, okay, so obviously that means you're differentiating cos x upon sin x. Okay, cot square x dot dx equals to cos square x upon sin square x dot dx. Okay. Okay, we know that the differential of cot x is this. That means when you're going to integrate the differentiation of cot x is cos x square x. Okay. Okay, we have the third identity here, which if you remember, 1 plus cot square x equals to cos x square x. Okay, so in place of cot square x, if we write cot square x, we know is equals to cosec square x minus 1. So what I'm doing is that in place of cot square x, I'm writing cosec square x minus 1. Okay, I have to apply the boundaries of pi by 2 and pi by 4. Now we know that from here, if you notice, if y is cot x, dy by dx is this. That means if you're going to integrate this, you will get this. Okay, when you're going to integrate cosec square x, I'm writing it down here. Integration of cosec square x, negative cosec square x dot dx is going to give you cot x. Okay, so if you want cosec square x only, integral of this, it will be minus cot of x. Okay, so it will be minus cot of x minus x, and then you have to put the boundaries, pi by 2 and pi by 4. Okay, minus cot of pi by 2 minus pi by 2 minus cot of pi by 4 minus pi by 4. Okay, let's simplify this. Tan of pi by 2 is undefined, so 1 upon undefined is going to give us a 0. Okay, basically tan of pi by 2 is equals to undefined. We know that tan goes up to, if you use the graph, okay, if this is pi by 2 and this is pi, you draw a dotted line here and the graph goes up like this, it goes to infinity. So tan of pi by 2 is infinity. So cot of pi by 2 is going to be 1 upon infinity, and 1 upon infinity is always equals to 0. So minus pi by 2 here, the first bracket, minus cot of pi by 4. It will be minus 1. Tan of pi by 4 is 1. So the reciprocal of 1 is also 1. And since it's a negative sign before this, so minus tan of pi by 4, which is minus 1, minus pi by 4 here. Let's simplify this. Minus pi by 2 plus 1 plus pi by 4. Pi by 4 minus pi by 2 is pi by 4 plus 1. Okay, negative pi by 4 plus 1, because pi by 2 is a bigger number. This is the answer to this question, which we have proved. Now they're saying express 2x in terms of cos of 2x in terms of sine square x, and show that 1 minus cos of 2x can be expressed as, okay, I'm just taking this whole part down here. Express cos of 2x in terms of sine square x. We know cos of 2x equals to 1 minus 2 sine square x, and hence show that 1 minus cos of 2x, okay, if I make sine square x the subject from here, we know that sine square x is going to be 1 minus cos of 2x divided by 2. Okay, so 1 minus cos of 2x equals to 2 times sine square x. Okay, so they are saying express it in sine square x and show that 1 upon 1 minus cos of 2x can be expressed as this. 1 upon 1 minus cos 2x, we know 1 minus cos 2x is equals to 2 sine square x. So I can write 1 upon 1 minus cos 2x equals to 1 upon 2 sine square x, which is actually 1 upon 2 cosec square x. Hence, using the result of part 1, find, okay. Okay, you have to integrate you have to integrate 1 minus cos of 2x, which we know dot dx, which is equals to half cosec square x. That means now we have to integrate cosec square x. You have to use the result of part 1, which I am just copying from here. Okay. From here we know that if y is this, dy by dx equals to this. That means if you're going to integrate cosec square x dot dx, you will get cot x. Okay, as a result, the negative, if I want to move from here, cosec square x dot dx is equal to negative cot x. Now, if I have to integrate this, half is already outside cosec square. In place of cosec square x, the integral of this is minus cot x. So I can write it is equals to half of minus cot x. Okay, plus c, minus half cot x plus c. Okay, so this is the answer to the third part of the question. We're done with this question. Moving on to this one. Find the integral of this. So I'm going to divide both of them by this. Let's see. It's 1 upon cos square 2x plus cos 4 2x upon cos square 2x. Okay, 1 upon cos square 2x can be written as sec square 2x. We're still doing the simplification, so I'm not removing the integral sign. Once you'll start with the integration process, then we're going to definitely remove the integration sign. Sec square 2x plus cos 2x upon cos square 2x will give you cos square 2x dot dx. Now we are going to start with the integration process. Sec square 2x. Sec square x, the integration of sec square x is 10x. Okay, I'm writing it here. Integration of sec square x dot dx equals to 10x. Okay, so if it is sec square 2x dot dx, it will be tan of 2x divided by 2. So I'm writing tan of 2x divided by 2 plus cos square 2x. We know cos square 2x. First of all, let's write cos square x here. Cos square x is actually 1 plus cos of 2x divided by 2. Okay, if I want to write cos square 2x, since I am doubling the angle here, I will have to double the angle here as well. Okay, so I'm writing cos square 2x is equals to half plus cos of 4x upon 2. Okay, what I can actually do in this step is, since I need to write, in place of this I have to write this and then I have to integrate it. What I'm doing is I'm copying this also as it is right now. 1 upon cos square, okay, I'm writing sec square 2x here. Okay, so I'm copying it as it is because I'm not starting with integration. In place of cos square 2x, I'm going to write half plus half of cos of 4x dot dx. Okay. Sec square, now I can start with the integration process. The integration of sec square 2x is going to be tan of 2x divided by 2 plus integration of half is half x plus integration of half cos of 4x. Integration of cos is sine of 4x divided by 4. Okay, so it's going to be half tan 2x plus half x plus 1 upon 8 sine of 4x. Plus c. Okay, without using a calculator, find the exact value of the integral of this, giving your answer in the form ln a e to the power b, where a and b are integers. Okay, you have to integrate this in the second part of the question. This is the second part. Okay, integration of 2 is going to be 2x. Okay, this will be done with ln. The differentiation of this is 3. Okay, instead of a 3, I have a 6 here. That means that 2 is extra here. Okay, so I can take it out and then I can write ln 3x minus 2, and then I can put the boundaries of 14 and 4. Okay, we don't have to use a calculator here. 2 times 14 is 28 plus 2 times ln 3 into 14 is 42 minus 2 is 40. Okay, this is the first bracket, minus 2 into 4 is 8 plus 2 ln 3 into 4 is 12 minus 2 is 10. Okay, 28 minus 8 is 20 plus 2 ln 40 minus 2 ln 10. 20 plus 2, if I take out as common, I'll be left with ln 40 minus ln 10. 20 plus 2, ln 40 upon 10 can be written as 40 upon 10 using the quotient law. 20 plus 2 ln 4, 2 can become the power. 20 plus ln 4 square is 16. Okay, you have to give the answer in this form. Okay, if I want to introduce ln here, I can write 20 ln e plus ln 16. This will become ln e to the power 20 plus ln 16. Okay, since they are being added and the same base, that means log to the base of e in both the terms, I can add them using the product law. ln 16 e to the power 20. Okay, that means a is 16 and b is 20 in this question. Okay. We don't have to write this down. This is the final answer basically. The next question number 14 now. The diagram shows the curve y equals to x sine x. Okay, I think let's just wind this up and we'll do this question once we do integration by parts. Okay, so let's wind up this. Thanks a lot for watching the video.